All right, so question 27 dealt with a second edition postulate question. Now, this is the second time that this has shown up in an assignment. And I just want to kind of point things out to you. When I do things like that, I'm trying to get your mind set on what you might see on a test or a quiz. Okay? So I thought this question was hard initially, to where it didn't maybe belong on the quiz on Friday, that some of you still need to take. If you weren't here on Friday, you need to come see me so that you can schedule that. Okay? It was maybe a little bit more difficult for that quiz, but the test for this chapter or the next quiz, if we have another one, since we've talked about it twice, would be maybe fair game for that. Okay? So the thing here is, it says, use the diagram to the right and write an algebraic expression for G to K. So I need to write an algebraic expression for G to K. So we need to add some things together to end up finding that distance right there, correct? Okay. Would you guys agree that I'm at least going to use that there? If I were to stand right there and walk to J, I've walked part of the green. So 3x plus 3 must make up some of that green. Okay? Now, when I get there, when I've walked, whoops, the select tool doesn't really want to work very well here. All right, so if I walk from there to there, okay, and now I'm standing right there, I need to walk the rest of what ends up being that distance right there. Does that make sense? Okay. Now, I can't call that 5x minus 2, right? Because 5x minus 2 is bigger than that blue section that I just highlighted. But how much bigger is 5x minus 2 than that blue section that I just highlighted? It's that much bigger, right? So what does that translate to? It's that distance, isn't it? So does it make sense that this blue section here is it's not 5x minus 2. Would you agree that it's 4x minus 2? Does that make sense? Okay. So I'm going to take the yellow of 3x plus 3. I'm going to add into it 4x minus 2. And that should end up being my algebraic expression for GK. Now you're going to want to simplify that. You're going to want to write that as 7x plus 1 is equal to GK. GK 7x plus 1. Now it says, well, if GK is actually 50, can you find GH and JK? Okay, so GK is actually 50. Subtract 1 from both sides, you get 49 is equal to 7x, right? X is 7. Plug things back in. Let me just erase some stuff here real quick. If I plug into that, if I plug 7 into that, which would be, what, 21 plus 3 would be 24. If I plug 7 into that, I get 35 minus 2, which would be 33, correct? And this distance here would be 7. So when I'm asked what is G to H, G to H is not 24. I stop how many units short of 24? I stop 7 units short of 24, right? So that should mean that G to H is 24 minus 7. So it should be 17. Is that right? Okay. So G to H is 17. We know h to j, that was x, so that's 7. Okay, now we can do one of two things, and I'm going to kind of use this approach here, where if I want to find j to k, that distance there, okay, it's, again, 7 units short of 33. What's 7 units short of 33? 33 minus 7 would be 26, isn't it? Now, the reason I want to go that approach is because now, as I went that approach, I never focused on the number 50, right? If I take 17 plus 7 plus 26, does that give me 50? Which they said was the length of G to K. Okay? You've got overlap. Okay? It would be real nice if I could just use 3x plus 3 plus 5x minus 2. Set that equal to GK. But there's an overlap there. If I were to do that, and this is maybe an alternative way of, it's the same math, but it's an alternative way of maybe thinking about it. If I were just to write 3x plus 3, plus then, so I'll put that in parentheses, plus then 5x minus 2, and set that equal to GK, do you see how in the 3x plus 3, I incorporate that distance? And in the 5x minus 2, I incorporate the same exact distance. So when I write 3x plus 3 plus 5x minus 2, I've actually incorporated that distance that I circled up there 2 times. If I walk from G to K, I don't walk HJ twice, right? I should only walk HJ once. So I need to remove HJ out of there. And I can do that this way. And now if I add like terms, 3x, 5x, minus 1x is 7x. 3 minus 2 plus 1, and I can get GK that way. It's a different maybe way of thinking about it or writing it down, but logically, it's the same argument as what we did when I was highlighting the segment. Does that help? Okay. Any other questions on there? I'll give you like a clock or something. Okay. Okay, so it says mine says find the smaller angle measure of the hands of a clock at a given time. So 9. Let's see if there's any other. So 9 or 6. 2. Do a couple of these. Yes.
90 degrees.
Yeah. How'd you do it?
Well, you take the clock.
Yeah.
And then you put one hand on 12 and one on 9 and you do the right angle.
All right.
90 degrees.
Well, what if it was 2 o'clock?
Then you take the clock and you put one on 12 and you put one on 2. And then you got to figure it out.
Okay. This would be 12 o'clock, right? We've got 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock. So that's our clock, right? Okay. So anything that was 3 o'clock, 9 o'clock, would have been giving me, like Skylar said, we have something like that, right? And that's a right angle. If it was 9 o'clock, that hand would be over here, and that would be a right angle, okay? But what if it was 1 o'clock? You'd have your minute hand there, and then your hour hand pointing there. How do I do that? Huh?
Is it 30 or 60?
Okay, so that angle there would be 30 degrees.
No, it's 30 degrees, right?
So here's the logic, okay? Because each hour is comprised of 60 minutes, right? Each hour is comprised of 60 minutes. So the spacing The space between 12 and 1 is the same space between 1 and 2, right? It's the same space between 2 and 3. If I take and just draw the different places my hour or minute hand could be all the way through, I would draw 12 different rays that are going to those numbers, right? How many degrees are there in a circle? 360, right? I'm going to break that up into 12 equal increments. So that's where I get my 30 degrees. So that means each one of these, so that there, that's terrible. So that angle there is 30 degrees. This angle here is 30 degrees. That one is 30, and so forth all the way around. Does that make sense? So then when I got to figure out what time it is, everybody tell me a time, then I just got to figure out how many of those 30-degree angles are in my particular circle for my time. So if they said, now, they did make it easy on us in regards to this question. This question could get a lot more difficult, like intensely difficult. But if I say like 5 o'clock, okay, so my hour hand would be there, my minute hand obviously there. So now there'd be a 30 there, another 30, another 30, and then another 30, right? So 1, 2, 3, 4, 5. 5 times 30 is 150, correct? Okay. Now the reason they say like the smaller angle, if you look up here, guys, there's an angle between these two right here, right? And that angle is going to be pretty close to 180 degrees right now. Let's do it that way. So let's say that angle right there is like 120. This angle here would be 240. Does that make sense? Okay. So we can have angles that are bigger than, yeah, we're not going to know what time it is now. But we can have big angles that are bigger than 180 degrees. We're just not going to talk about them yet. So that's why they tell you in the directions, use the smaller of the two angles that are created. But does that help? Does that make sense? Okay. Now, you're on track, hopefully, to take college algebra and trigonometry later on in 11th grade, 12th grade. When you get to those courses, what we do is we ask, what's the angle when it's not 5 o'clock, but maybe it's 5:28? Okay? Because when it's 5:28, there's a lot of things that are happening there. Okay? Obviously, the minute hand has moved away from 12, right? Okay? But what has happened to the hour hand as well? It's moved. Okay? It has moved almost halfway between 5 and 6, right? Okay? So we kind of deal with how that adjustment should take place and how we deal with that mathematically. But we should be able to still find that angle.
What's your guess for that one?
So 520, it'd be pretty close. It'd be very small. Huh? Say it again. Well, one can't be at 12, and the other one be at. So when I've got my.
Oh yeah.
So the 12 one is going to be pointing to the. So this blue one here. It would be pointing. Like if it's 5:28, like it's almost there, right? And the hour one would be there, but we should be able to eventually figure out what that angle is based on understanding there's 360 degrees all the way around, so that's 28, all that kind of stuff. But it's a little bit longer of a process than what we just went through. Are there any others on that assignment that you guys maybe feel uncertain about? Were there any with the actual angle addition questions that were troublesome? Anything with the protractor? Any of these? Nobody? What do I set that one equal to? Yes, I got to add those together and set them equal to 90. What about this one here? It says I have got a
180.
Straight angle, good. So I'm going to add those two expressions together and set it equal to 180, and then go through that algebra. Okay. The one thing I want you guys to kind of pay attention to and kind of hone in on, this is your education, right? I already know how to do all these. If you don't know how to do one of them, you need to express that to me, okay? And don't be afraid that, I'm the only one asking questions, because if you have a question, guarantee you somebody else has the same question, you're just a little bit more shy to ask that question. So ask this question. As I told last class, you know more about what you don't know than what I know about you. Does that make sense? Okay? You know more about what you don't know. Okay? You know more about that. Things that you don't know, you know more about it, right, than what I do? Sure. On your homework. Does that make sense? Okay? You know what you struggled on. You know what you excelled on. Okay? And you know that a lot quicker than what I can gain from you. Okay? I will eventually learn what you struggled on, but usually when I learn what you struggled on, I don't want to say it's too late, but there's been some assignments that have accrued, maybe negative performances on that we could have avoided if you would have voiced that opinion, voiced those concerns earlier. Is that okay? So this is your education. You guys decide. You drive the class. Okay? You make the decisions for me on, do I go on to a new section today? Do we talk a little bit more about these questions? Do we spend more time on old information? That kind of thing. Okay? But if I get nothing to me equates that we all understand what's going on and we're going to ace the next quiz or test. Okay? Does that make sense? So please don't hesitate to ask questions. That's what they pay me for. So we're okay? All right. What I would like to do is get into section 1.5. Now, we're not going to be able to finish it today. But we will start it. Promote subpage. All right, so 1.5 is called exploring angle pairs. When you see the word pairs, what does that bring to mind? What? Set of two, okay? So everything we talk about today, you're going to see in the definition the idea of two, okay? And then I will present you questions that maybe somewhat contradict the pair of two, but still match up to some of the things that we see in our definitions. And I want to ask you to be able to analyze my statement and tell me whether it's true or false based off of definition. Okay? One thing about definitions real quick. Okay, I'll let you write the first one down here. Okay, we're talking about pairs of angles, so sets of two angles. So this says adjacent angles are two angles, so there's the pairs concept, that share the same vertex, they share a common side, okay, which is going to be a ray, and they have no interior points in common. So the word common means they share it, right? So Hunter and I have something in common. Very good-looking gentleman, right? Okay? But common, whenever we see the word common in this class, in math class, English class, and comparing like characters or something like that, commonalities are things that are shared. Okay? So those are three pieces of criteria that need to be met before we can classify something as, or a pair of angles as adjacent angles. There's a lot of geometry that you guys are going to use once you leave high school and you buy a house and you start doing construction on that house or repairs or maintenance or whatever. You might have to do some geometry. Okay, I had to replace some of my drain pipes in my basement. They're putting a new sewage system in my subdivision, and I had to be up to code with my washing machine to do this. So I had to use some geometry so that I didn't have to pay a plumber to come out to my house. He quoted me at $1,800 to replace something that cost me $44 at Lowe's. Okay, so I don't want to spend $1,800 on a $44 fix, right? So I'm going to maybe use a little bit of geometry so that I can do that stuff effectively. Okay, so you're going to use a lot of the stuff that we talk about in here later on. Okay. In addition to the facts and concepts of angles and that kind of stuff that you use later on, the way that geometry starts to program us and the way we think about mathematics is going to be used a lot quicker than maybe 10 years from now when you buy a house. It'll be used next year, in the following year. Geometry gets us to reprogram the way we think about math. Okay? If we can start thinking about math in regards to properties, definitions, rules, and how those things interrelate, intertwine, and how one rule coupled with a second rule generates a third one, it's going to make us understand mathematics a lot easier. Okay? One of the main concepts that people struggle with in the past, and then when I was in your seat, it blew my mind, and I didn't have any idea what was going on because I neglected to take this approach, but it's to learn the vocabulary and to understand what a definition really does. A definition is something that allows us to categorize things. It allows me to put an object in a specific category. Does that make sense? So we've got freshmen, we've got sophomores, we've got juniors and seniors. Those are categories, right? And you have to meet a certain definition so that you get put in a sophomore category and not accidentally, unintentionally put in a junior category. Does that make sense? Okay, if there was something that allowed you as a sophomore to be unintentionally put and classified as a junior, and you got accidentally put into some junior classes this year, get told you had to take the ACT in February and that kind of stuff, that would be kind of upsetting to you. Okay, you got misidentified. Okay, we don't want to do that. All right. If I was in Africa and I was in a safari and they define a giraffe as a four-legged African animal, and I come across a black and white striped four-legged horse, I call it a giraffe. Is that right? No. I unintentionally, based on the definition of a giraffe, I unintentionally classified a zebra as a giraffe, right? That's a problem, correct? Okay? So in mathematics, when we write definitions, it's so that nothing unintentionally gets categorized, in this case, as an adjacent angle when it's not an adjacent angle. Because there will be things that we can do with adjacent angles that we can't do with other angles. So I don't want those other angles to actually be called adjacent angles and then unintentionally do the work that's supposed to be meant only for adjacent angles with things that are not. Does that make sense? Okay? So our definitions, they're written the way they are so nothing gets unintentionally classified. If we keep that approach, we understand that approach, I think this class is going to be a lot easier for you. That being said, if you don't know the vocabulary words, that approach is really useless to you. Okay? There's three, so our vocabulary words, our definitions, sometimes they're going to seem long-winded, but they're actually very concise. They're very, very to the point. And sometimes that, to a point, gets confusing. It gets, you read something and think, well, what did I just read? You guys do that with Shakespeare, right? In Mr. Silas' class, you ever read something, or any class, you're reading a textbook, and you read 5, 6, 7 pages, and then you look up and say, I've been reading for a half hour, but I don't remember a single thing I read, or know a single thing I read. Does that ever happen to you? I think when you see some of your vocabulary words in this class, that's going to happen to you. First time you read them, you read over, and you're like, what in the world? Okay? If that happens, you've got to stop, go back, reread it, take it apart, piece by piece, draw pictures, and then things will make sense to you. And you'll see that here in a couple minutes. But this vocabulary word has 3 pieces of criteria that you need to meet for angles to be considered adjacent. Okay? In everyday language, we say adjacent means next to. Okay? So right now I'm next to Skylar, right? You guys agree with that? I'm adjacent to Skylar. Am I still next to him? Still next to him? Still next to him? Some of you shaking no, some saying that. What about now? Am I still next to him? So some of you said yes here, but a lot of you said no here. Well, then what about right here? Or what about right here? So where is that cutoff from here to here that allows you to say, and I'm no longer adjacent to them? You understand how that's kind of a problem mathematically? I don't know if I say two angles are just angles that are adjacent, are just angles that are next to each other. What is the differentiating feature that tells me maybe these two angles are next to each other, but those two are not? Does that make sense? Where is the cutoff? Okay. Well, just saying that adjacent angles are angles that are next to each other is too vague in mathematics. It leaves it open to interpretation. So we have these 3 points of information that need to be satisfied. You have to have the same vertex. Having the same vertex meets the first piece of criteria for adjacent angles. You have to share a side, and then you have to have no points in common, no interior points in common. So when I look at this picture here, do these two angles share a vertex? No, right? Okay. Do they now share a vertex? They do now share a vertex. Do they have a common side? No. Okay. These are separate sides here. Okay, so side W and side V here are separate. They're not shared. Do they have any points in common? So when I color all these interior points here for this blue angle, should be all these points in between these two rays. Same thing over here. So those angles meet two pieces of criteria. They have the same vertex. They have no interior points in common, but they don't share a common ray. So those two angles are not adjacent. Okay? Your adjacent angles are ultimately going to look like these. And I've done a little bit too much there. So your adjacent angles are going to look like that orange one and that blue one. If we look at those, do they share a vertex at C? Do they share a ray that goes from C to F prime? Okay, I don't know if you've known that notation or seen that notation before. It's the way GeoGebra operates, and it's the way some of your homework will operate. Notice that point right there is called F, right? Well, this one uses F as well. So if they were both just F, and I said, everybody look at F, so I'm going to look at the bottom one, so I'm going to look at the top one, right? But you see that top one has an apostrophe after it. It kind of looks like this. If I were to zoom in, it looks like that. Okay? Well, that's different than F, right? So now I have a feature that can differentiate and make sure you are looking at the same one. But we read that, instead of F apostrophe, we read it as F prime. Okay? There's a second one up here. Right here, it looks like this. If you were to zoom in, and that's F double prime. Okay, so it allows me to use the same letter over and over again if I want to. Okay, so there we see that they share the same vertex C. They have the same ray, C to F prime. And do any of the blue or interior points overlap the orange ones? Or vice versa? Do any of the orange ones merge into the blue? No. Okay? So that is a set of adjacent angles, and all your adjacent angles are going to look that way. Okay? Now, obviously, we can change the size of them. Okay? But, traditionally, they're going to look like this. And a lot of times, so this is a set of, like, adjacent angles that goes beyond 180 degrees, which is, we see them from time to time. But early on, most of your adjacent angles are going to be kind of like that, where they're two acute angles. But that's not, I don't want to say acute, but they're two angles whose sum is less than 180. That doesn't have to be the case. It's just what we see early on. When we talk about things that are adjacent angles, or just any vocabulary word, I think it's important to not only talk about the things that are those vocabulary words, but to see examples of things that are not. Okay? So that first one we saw, that looked like maybe kind of looked like that. Okay? They meet two pieces of criteria. They have the same vertex. They have no points in common, but they don't share a common ray. So those are not adjacent. Okay? If I did something like that. Okay? You see how right here we started overlapping points. Okay, kind of in that middle section. You got blue points on top of orange points. So that's showing you have common interior points. That violates the definition of adjacent. You still have a vertex that's the same. Do you share a ray? In that situation, you do not share a ray. There's 4 total rays, right? Okay. For adjacent angles, we'd only have 3. Let's look at the last situation that we come across sometimes is something get that point. Just come down. About as close as I can get it. Would you agree that none of the orange points overlap the blue points? So no points in common there, right? No interior points in common. Do they share a same ray? Does one ray make a side for both those angles? Yep. Okay. Now, I wouldn't identify it as, that blue angle is going to have like ray AB or AD. I think it's D up top. And then the orange angle would have ray BD. So because they start at different vertices or different endpoints, we probably wouldn't call them the same ray. So that maybe is a violation to some extent. But there is one ray that plays a role in creating both sides, or one side of both angles. No interior points in common. Do they share the same vertex, though? No. So at any time you violate one of those 3 conditions set up in the definition, you no longer have the type of angle that definition sets out to provide us. Okay? Now, we spent a lot of time talking about that definition. Okay? And I always spend time on things that I know are important for the rest of this class. Okay? We will talk about adjacent angles from here on out for the rest of the year. Okay? So it's very important that we understand what they are, how to identify them, and then the things that we can do with them. Probably the second most used pair of angles we ever talk about are vertical angles. And I hate this definition. Okay? This definition, and I don't like definitions that are of this nature. This is kind of what we call an existence definition. They show you how they exist, okay, or how they are created. Okay, where the last one gave us features of an adjacent angle, right? Okay, this one shows you how they are developed, how vertical angles are developed. And the definition is what's written in red up there. It says, are 2 angles such that the sides of one angle are opposite rays to sides of the other angle. 2 angles whose sides of one angle are opposite rays to the sides of another angle. And something that's going to play over and over and over throughout the year is that when we're building our system of mathematics and we're creating these vocabulary words, these definitions, those definitions are going to be used to create other definitions. So if I don't know what opposite rays are, I'm going to struggle being able to determine what vertical angles are, right? Later on, when we see another definition that incorporates vertical angles, I'm going to have trouble understanding that. I didn't know what opposite rays were, therefore I didn't know what vertical angles are, therefore I don't know what the new vocabulary word is. Okay, so these things build upon each other. The best way, and this is once you see it, this is very simple. Okay, but I think reading the phrase is kind of confusing. But what we get at here, it says 2 angles such that the sides of one angle. So I just want to focus on the sides of one angle. I'm going to look at that side and that side of angle 1. Do you agree that those are sides of angle 1? Okay. If we have vertical angles here, what they're saying then is that those 2 sides that I just highlighted are opposite rays with another angle, meaning that they form a straight line individually with another angle, or the sides of another angle. So I'm going to take angle 3. I'm going to highlight its sides blue. So you got the red angle and you got the blue angle, right? The red angle number 1 and the blue angle number 3 are what we call vertical angles. If we look at the red and blue solid lines, we would agree that they are sides for respective angles, right? Red one for angle 1, blue one for angle 3. But are they, the solid ones, are they opposite rays? Okay? So those two, red ray and blue ray, the solid ones, serve as opposite rays and as sides of two angles. What about the dotted ones? Are they opposite rays? So we have a situation here where we've got two angles, angle 1 and angle 3, where the sides of angle 1 form opposite rays of the sides of angle 3, or vice versa, the sides of angle 3 form opposite rays of angle 1. And that allows us to create what we call vertical angles. The easiest way to think about this, guys, and able to identify vertical angles is what I've got written in black there. Simply says that vertical angles are always created when you have two lines intersecting. Always going to have vertical angles when two lines are intersecting. So that angle right there and that angle right there are vertical. Do they look like a mirror image of one another? Does that make sense? When you have two lines intersecting, you can find the angles that look like mirror images. They are vertical. Okay? Now, what do you think about when you hear the word vertical? What's the first thing that comes to mind? What directions? Up and down, right? Okay? That angle there and that angle there, they meet this definition. Okay? So even though they're not up and down, those would you probably think more horizontal there, right? Okay? Some pictures, nothing will look vertical, nothing will look horizontal. It'll be at an angle. Okay? Or it'll be rotated a little bit. But angle 2 and angle 4, angle 2's sides serve as opposite rays for angle 4's sides, and vice versa. So 2 and 4 are also a set of vertical angles. Okay? Vertical angles, adjacent angles, those things become very, 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 very important to us. We're going to use them over and over and over and over again. Okay? It's going to be important for us to identify them. Okay? It's not that hot. Well, you knew it was going to be 88 degrees today, so why are you wearing jeans and a long sleeve shirt? Ordered to? Did you guys do probability last year? Have you ever done probability? Kind of dabbled in it a little bit? What if I said that there is a 90% chance that it's going to be 88 degrees today? What's the percent that it's not going to be 88 degrees? 10%. You took 100% and you subtracted the 90 I gave you, right? So the fact that it's not going to be 88 degrees would be called the complement of being 88 degrees. Okay? Let's talk about it like rain and not rain. If I say it's 70% chance it's going to rain, what's the complement of that? 30%. Okay? So 70% chance it's not going to rain, 30% chance it is going to rain, right? So the complement, when I ask you what's the complement, event, and probability, it was everything else that could happen, right? Does that make sense? Okay? And when we added two complement events together in probability, they added up to 1. That's how we knew to find the other thing. Okay? What could have happened. Okay? When we talk about complementary angles, that word complement is still in there. And it means the same type of idea. Okay? But it doesn't mean we're going to add up to 1 now or 100%. It means we're going to add up to 90 degrees. So complementary is a set of two angles who have the sum of 90 degrees. One angle is referred to as the complement of the other. So when I ask you if one angle is 40 degrees, what's its complement, or what is everything else that could happen, how many degrees am I leaving out? 50. So 50 would be its complement. Does that make sense to everybody? If I give you an angle that's 30 degrees, its complement is 60, right? Okay? We're looking for two angles that add up to 90 degrees. If you know one of them, you should know both of them. Okay? Complementary angles says nothing about them having to be adjacent, correct? Says nothing about any orientation, how they need to be attached to one another or apart from one another. So we see two pictures down there where we got one situation with the red angles where they are adjacent, and we got a picture with the black angles where they're not adjacent. Okay? So what if I did this? What if I said I've got that angle, let's say it's 30 degrees. Let's say I've got that angle, let's say it's 40 degrees. And let's say I've got that angle is 20 degrees. What do those add up to? What's 30 plus 40 plus 20?
30 or 20?
30 plus 40 plus 20. 90, right? Are those three angles complementary? They add up to 90. Why not? The definition complementary specifies that it can only be two angles. Okay? So those we wouldn't refer to as anything other than just three angles that add up to 90. Okay? There's no special word for them. Is that okay? So complementary has to be two. They can be any orientation. They can be attached. They can be unattached. They can be adjacent. They can be overlapping. Okay? They have to sum to 90. Two angles that sum to 90. Okay? So guys, and I know, so this is going to be something I just want to kind of nip in the bud before it happens. So all the other classes today, guys, they get 48 minutes or whatever, and that time, 48 minutes, is not expired for us. We've got a little bit of time yet. Okay. So if I go up to the bell, don't start putting stuff away until we're done.
To congratulate our 2019 homecoming court apprentice. Freshman class is Alexandria Renner and Brenton Sharp. Sophomores is Samantha Singer and Britton Hall. Juniors is Kriya Ackerman and Trey Johnson. Seniors is Lucia Vilo, Alex Davis, Emma Dieters, Cody Metcalf, Austin Stiggs Miller, and Nathan Hardesty. Thank you.
All right. So we'll finish up with we'll finish this one here. Supplementary angles, two angles to add up to 180. Okay? So it's the exact same definition. It's just a different result. Instead of adding up to 90, supplementary adds up to 180. Okay? Is that okay with everybody? You're going to mess those up. People will mess those up. This is the way I remember. What letter comes first, C or S in the alphabet? C comes first, right? What number comes first, 90 or 180? 90 comes first, right? So C pairs with 90, S pairs with 180. Alphabetically and numerically, they respectively come first. C and 90, S and 180. Is that okay? Okay. They do not have to be attached. Okay. They do not have to be on the same page or even in the same plane. They're just simply two angles. When we add their measurements together, we get 180 degrees. Okay. Last class got a little bit further than you guys did. So we'll catch up with them tomorrow. There's no homework this evening. Okay. Finish this tomorrow, and then hopefully have some time to work on your assignment tomorrow.